Good evening, everybody. So, today how we will construct the involvement of pi orbitals that we will see. In our last class, we have seen that sigma bonding interactions were useful in certain sets of metal orbitals and the corresponding matching ligand orbitals. So, there we have seen that if in a particular orientation the px orbitals from all the ligand systems, that means the L having their px orbitals and they are basically pointing towards the metal center, can form some overlap with the corresponding symmetry level orbitals available from the metal ion. So, that gives rise to the corresponding sigma interactions between the metal and the ligand. So, based on these, what we can find from there, that whatever interactions we are having and the corresponding interactions what we get due to only the sigma bonding interactions is the corresponding ordering of the ligand strength. So, we can have some idea about the ligand strength, that particular ligand strength in terms of the sigma bonding interactions. These sigma bonding interactions can therefore tell us the corresponding strength of these different ligands. So, if we can have some ligands like L1, L2 and L3. So, first thing what we have to judge is the corresponding nature of these ligands. So, if they are of same type and if they are only can be termed as the sigma donor ligands, then in terms of these pi bonding interactions we can arrange these sigma donor ligands utilizing this corresponding ligand field theory based on the sigma bonding interactions. But when we consider the other sort of interaction, because the sigma bonding interaction is not the only interaction which is taking place with the metal and the ligand, and some interesting interactions we can have from these pi orbitals. So, we must have some choice for the remaining orbitals which are available from the ligand set, that means the corresponding px and the py orbitals, though they are not directly facing the corresponding metal ligand axis, but they are in some other orientations. So, they will give the corresponding pi interactions, whereas these head on overlap between the px and the suitably placed metal orbitals can give rise to corresponding sigma interactions. So, in today's class what we will see that how these orbitals can be chosen, and from the group theoretical treatment related to the reducible and irreducible representations for these orbitals, we will find out how we can get the corresponding symmetry group orbitals for pi interactions, or rather the symmetry adapted linear combinations. So, symmetry group orbitals and the symmetry adapted linear combinations are therefore useful when we talk in terms of the corresponding pi interactions. So, these interactions are also useful. We will see that in this particular case the ligand can be sigma donor ligand, and there can also be some possibility where we can consider these ligands as that sigma acceptor ligands also, when the metal is present in low oxidation state or in low oxidation states, particularly the 0 or +1, when most of these orbitals present on the metal sides are filled, Then if there is some vacant orbital, that means the lowest unoccupied molecular orbitals are available from the ligand side, then we can get some interaction where the electron density or the charge density from the metal side can be transferred to the ligand side. Similarly, here we will also consider this for the interaction as for the pi as well as the pi star level. So, in today's class, what we will focus our attention that how we construct these sigma and the sigma star orbitals, because we know from our school days that there are some ligands which we considered as the pi acid ligands. So, once we know these ligand field theory related to pi interactions, then only we can have some idea that what are these pi acid ligands, because so far in terms of the corresponding crystal field theory and the basic ligand field theory for sigma interactions, we have not encountered any such orbitals where we can talk about something where the interaction is of pi type. That means these interactions what we are talking all the time, that is the corresponding metal and the ligand interaction, and the interaction is pi type. So, how we can get these pi type interactions involving those ligands which are of special type completely different from the sigma type ligands, they will interact with the metal involving some other orbitals from the metal ion side. So, today's class will just treat these pi bonding interactions for the corresponding ligand field theory. So, this particular theory again will tell us that how the ligand in terms of not only the sigma bonding interactions, but also pi bonding interactions can give rise to the corresponding ligand field surrounding the metal ion for a particular symmetry. So, the treatment what we are doing only for the very well known symmetry, that means the octahedral symmetry. So, in a similar treatment we can have the other symmetries as well. So, the first thing what we should have for this treatment is the corresponding reducible representation for pi bonding. So, taking the help of group theory and its character table in octahedral symmetry, how we can find the corresponding this reducible representations for pi bonding. It is nothing but a set of Cartesian coordinates for the establishment of each of the ligands. So, we have the ligand and already we have spared one orbital from each ligand, such as the corresponding px orbitals for the sigma type of interaction. So, the remaining orbitals can be utilized and its corresponding Cartesian coordinates can be utilized to know their symmetry level for pi bonding interactions with the metal centers. So, the direction of the sigma bond is arbitrarily set as the y axis, that means all the py orbitals are taken out from the ligand set, and these p orbitals from all the different ligands, that means if there are 6 ligands for octahedral symmetry. So, 6 py orbitals from 6 ligands have been taken out for the sigma bonds formation with the metal center. So, the remaining px and py orbitals should be used for pi bonding interactions. So, this is the corresponding orientation of these orbitals, and once we know the corresponding symmetry level for the orbitals which are available on the metal side. So, in this particular region the corresponding orbitals what are there, and already we have considered the head on overlap with the py, this py, this py, this py and that py for sigma bonding interaction. So, the other two orbitals, the px and py, which are perpendicular to this y axis for this individual ligand system, is considered for the corresponding sideway overlap for the pi interactions with the metal ion orbitals. So, we consider these two orbitals, and on each of these ligands for the combination of this px and y from each 6 of these ligands. So, altogether we will have 12 orbitals. Now, the number of orbitals are more, but the corresponding strength of the interactions, that means the pi type interactions are all the time we know, as we know for the CC interactions or CN interaction or NO interaction, that pi type interactions are always weaker than the corresponding sigma type interactions, but in this particular case the large number of pi orbitals can give rise to some characteristic feature of this assembly where we can have the corresponding metal and the ligand. So, if we consider this interaction as the simple metal ligand interactions, and we will find out that if the ligand in our hand is the corresponding simple carbon monoxide molecule, because large amount of our discussion we are concentrating our attention on this particular molecule, which is a very neutral one, but it is providing a very strong interaction with the metal. So, it is not that only the sigma interaction can give rise to the corresponding strength of enormous magnitude to this carbon monoxide molecule, but similarly if we can have the simple acetylene molecule, that what we are talking about, that we can have the corresponding carbon-carbon bond and we have the corresponding hydrogen atoms attached to these two carbon atoms. So, in this particular case also, because we can have this situation, we already know that for the CC bond we have the sigma bond and we have the pi bond. So, in this fashion not only the corresponding shape and size of these orbitals, which can be defined as the corresponding available pi orbitals from the ligand side. So, if we have the ethylene as our ligand, and therefore, we can have two pi type of orbitals already present in the molecular orbital picture of the ethylene molecule. So, we have the pi star and the pi orbitals present in the ethylene molecule. So, what we see that in a sense we can find out some interaction with the metal orbitals, where this pi orbital containing some electrons can be used as the donor orbital to the metal center. So, we can have a pi donor ligand of ethylene, and if the vacant orbitals on this ethylene molecule, which are of pi star type, can accept some electron density from the metal side, we get the corresponding acceptance from the pi star level, that means the corresponding LUMO level of the ethylene molecule. And this sort of bonding properties or the bonding picture is very useful, because not only the corresponding isolated metal complexes, like we can have the simple Ml6 molecule, and we are talking so much about this Ml6 molecule for the formation of sigma bond and the pi bond, but interestingly we will just consider some of these organic transformation and some more organometallic complexes, which we will not be discussing in this particular class, but we should have some good idea about these, that when a particular organometallic compound is forming, that means we should have a corresponding metal carbon interaction, that means metal carbon bonds are present. And if we get some metal as the corresponding catalyst, it can be present in some industrial catalyst or some biological catalyst, where metal is interacting with some of these carbon centers or some of these pi or sigma electron density available from these molecule, or say much more bigger molecule like benzene or cyclopentadiene or anything like that, where we can have some weak interaction during the catalytic process between the carbon center and the metal center. So, we should have the type of interaction what is taking place during the formation of this organometallic compound or the catalyst. So, we have the catalysts, and if it is a metal based catalyst, and if we have the corresponding substrate, so substrate we can consider as the corresponding ligand. So, this metal which is functioning as a catalyst or with some other ligand also. So, the metal complex can function as the ligand. and some other L which can also be functioning as the substrate. But if we have some interaction between this M and this L, we should have some clear cut idea whether the ligand field picture of this interaction can also be presented nicely for their electronic structure and the electronic properties related to this corresponding reactivity. So, the number of pi orbitals which were available for this system is very important. So, on each ligand site we have 2 orbitals available. So, 6 into 2, that means the 12 orbitals we can have in our hand, and those 12 orbitals will have some matching orbitals from the metal ion site. So, the reducible representation, that corresponding gamma tau, the tau gamma of pi for this corresponding reducible representation, which is for the pi interaction. So, the corresponding symmetry operation E is therefore 12, and we have the corresponding C2 and all other contributions in terms of the corresponding overall corrected table, where these symmetry elements all are present in the octahedral corrected table. So, this number 12 is nothing but the 12 orbitals which we are using for the construction of the pi interactions with the metal center. So, these 12 orbitals will now be involved from the ligand side for the formation of pi bonding interactions with the metal salts. So, how these pi interactions will be taking place with the metal d orbitals we can see. So, in our previous case, that means in our consideration for sigma bonding interactions, where we have seen that we do not have any matching orbitals for these dx, dxz and dyz orbitals, and they remain during the sigma bonding interactions. They remain as non-bonding orbitals from the metal side, and we can have the corresponding electronic transitions or the charge transfer transitions from the T2G level, which is of corresponding non-bonding character, and we use that particular level, and the unpaired electron density from those levels can be transferred to the Eg star level, that means the anti-bonding Eg level, and some other higher energy orbitals during the corresponding interactions of sigma bonding type. So, we have stated already that these are the orbitals that are non-bonding when we only consider the sigma bonding interactions. So, when we come to pi bonding interactions, they are of different symmetry which are perpendicular to some of these bonding axes. So, they will not remain as non-bonding when we consider the corresponding interactions which is of pi type. So, each of the 6 ligands therefore have 2 pi orbitals, that means 2 orbitals have pi symmetry, and there are 12 in total, and the symmetry adapted linear combinations, that means the SALCs of these fall into 4 triply degenerate irreducible representations, one of which is of T2G symmetry. So, what we have seen that we have the reducible representation. So, irreducible representation will now break into corresponding irreducible representations. So, we now find from the reducible representation the number of irreducible representations and their symmetry level. So, that is the next duty what we can do to know about the corresponding pi bonding interactions, what can form the different pi interactions with the metal and the ligand. So, one of the irreducible representation will be of T2G symmetry, that we can firmly predict from the corresponding symmetry level of these orbitals, what we all know in terms of crystal field theory or the ligand field theory, that these 3 orbitals which are in between the 3 Cartesian axes x, y and z has T2G symmetry. So, therefore, they will have some matching symmetry with the T2G symmetry from the ligand side. So, one of the irreducible representation within the reducible representation of this group of pi symmetry will have a similar symmetry which is T2G. So, these 3 orbitals will have the same symmetry, and pi bonds will therefore be formed between the metal ion orbital and the 6 ligands, and also have it that these pi bonds are just formed by the overlap of two sets of orbitals with T2G symmetry. So, if we go for the matching symmetry, that means the ligand will provide one T2G symmetry, that means the ligand group orbitals or the symmetry group orbitals can provide the T2G symmetry, which will have the corresponding matching symmetry with the dxy, dxz and dyz orbitals. So, we find that this irreducible representation, the corresponding tau pi reduces to T1g, T2g, T1u and T2u. So, only the T2g is matching with the corresponding ligand orbital. So, others are of different type. So, we have this is triplet 1, this is triplet, this is triplet and all 4 are triplets. So, will together we will have 3 plus 3 plus 3 plus 3, that means 12 orbitals which we are utilizing for the corresponding interaction with the metal orbitals. So, the T1g and TUD group orbitals are of the ligand do not have the corresponding symmetry of any of the metal orbitals. So, T1g and T2u are just therefore not matching. So, T1u set has the same symmetry as the Px, Py and Pz orbitals on the metal ion. So, these orbitals are used primarily to create the sigma bonds to the ligand. So, out of these 4, the T2g what we are taking is for the 3 d orbitals, and the T1u set what we know, the T1u set what we have seen for the sigma interactions also, that means the corresponding tau sigma, that means the reducible representations for sigma interactions, we have seen that there also T1u symmetry was there, and that T1u symmetry is utilizing the corresponding Px, Py and Pz orbitals from the metal ion. So, these 3 orbitals have already been used up for sigma bonding interactions from the metal side. So, though this T1u set of orbitals are available from the metal side, but they have already consumed for the corresponding sigma bonding interactions. So, we have these 2 plus we do not have any matching orbitals which are T1g and T2u type. So, the T2g set has therefore the symmetry of dxy, dyz and dxz orbitals on the metal ion. So, therefore, we have the main source of pi bonding is between the dxy, dyz and dxz orbitals on the metal and the dp or pi star orbitals on the ligand. If the ligand are of different type, they are not providing only the p type orbitals. If they are having some d orbitals also, that means if we go down from nitrogen to phosphorus, that we all know that the phosphorus is a bigger atom, and the phosphorus based ligands what we can have therefore the filled d orbitals. So, they have these corresponding d orbitals. So, we all know that some ethylene diamine type of ligand where we can have this phosphorus, we can have the suitable substitutions, and one of the most important ligand is the triphenyl phosphine ligand. So, all these have the corresponding d orbitals, and these d orbitals can now have the corresponding participation for this formation of these ligand fields around the metal ion, and they do participate in some way if they are having some filled electron density. That means, these d orbitals on these phosphorus atoms are filled. So, the electrons from these d orbitals can be donated to the metal orbitals if they are vacant. So, we have p, that p already we have discussed these p orbitals like nitrogen, like oxygen. Then we have seen that whether we have the pi type of orbitals, then the corresponding pi star symmetry is already be there, and this can also be utilized for pi interactions. That means, the pi bonding can be possible if we have the pi star orbital, that means the lowest unoccupied molecular orbital from the ligand side. So, the ligand if have empty d or pi star orbitals and serve as pi acceptor ligand. Now, we will consider some of these ligand as the typical pi acceptor ligand or full p and d orbitals to serve as pi donor ligand. So, if we have the vacant or empty d or pi star orbitals, that means if we consider the corresponding nitrogen, if it can have, we can consider that it has the vacant d orbital because we do not have any electron in the d level for nitrogen or oxygen. But if they are available for some kind of acceptance for the pi type of electron density from the metal side, this is the metal ion and its dxy orbital which is being shown here, that is the corresponding x and y axis. So, the Cartesian axis involving the x and y and the lobes are pointing in between the x and y axis for the corresponding dxy orbital, and this is the corresponding positive lobe and these two are the corresponding negative lobe for this corresponding matching symmetry from the p side also. So, we have the matching symmetry for the sign symmetry also from the py of the positive lobe as well as the negative lobe for the matching one. And if we have the filled p orbital like nitrogen or oxygen where we have the filled p orbitals available and the d orbitals such as phosphorus, then these electrons should be donated to the metal vacant orbitals and they behave as pi donor ligand. So, this particular point we can have the situation that we can have both these two types of orbitals, that means or the corresponding ligands. So, ligands can be classified as good pi acceptor ligand if it has some empty or vacant acceptor orbital, or it can be the corresponding pi donor ligand. So, similarly what we have discussed so far for sigma bonding interactions, that it can also have sigma donor capability as well as sigma accepting capability, though sigma star orbitals are of pretty high in energy which may not be utilized for the corresponding acceptance of the electron density from the metal orbital. So, this is from one symmetry type involving the py orbital from the ligand side. Then we can have the other orbitals, that means the d type orbitals or the corresponding pi type orbitals. So, this can have the corresponding symmetry of d type or the corresponding pi type orbital, because what we have seen in case of the corresponding ethylene molecule, what we have seen that the corresponding orbitals which are available from these carbon atoms, when we have these matching orbitals and if we can have the corresponding overlap for these matched orbitals, we have the corresponding pi orbitals available for this and the pi bonding for the CC bond formation. But when the same thing is happening for the corresponding pi star orbitals, where we will see that these are basically not symmetry matched. So, they are basically not facing the corresponding attractive force between the corresponding symmetry of these orbitals. So, if we can have these, so these are not matched, but these are the matched symmetry level depending upon the availability of the electron density for these orbitals. So, what we find that instead of these, so this can also be considered where we can have the pi star orbital, that how we can consider this as a corresponding equivalent symmetry lobe, or the lobes for these orbitals is available for say corresponding dxy orbital. So, it has a typical match symmetry, that means pi star orbital will have the corresponding match symmetry with that of our dxy orbital. So, either this orbital, that means the pi orbital, that means the pi star orbital, or the d orbital can be utilized for this corresponding pi interactions with the metal orbital. So, this is one such pi type or the d type orbital like this, which is available from the ligand side also, and also another pi type, it can also be the corresponding d type orbital, which is matching with that of or the metal dxy, dyz and dxz orbitals. So, these are the corresponding sets of corresponding orbitals which are utilized for these pi interactions. So, this is one particular pi type interaction, this is another pi type interaction, and this is also another pi type interactions involving the ligand orbitals of pi symmetry. So, what we see therefore that the empty pi antibonding orbital, if we can have not only for the CC bonded species like ethylene, because why we are talking so much about this ethylene molecule, because the ethylene molecule is very interesting molecule for some of these reactions where this it can have some interaction with the metal center. So, we can have the metal which is interacting with the ligand as the ethylene backbone, and that ethylene backbone when it is interacting we can have this, or when it is functioning as a catalyst it can give rise to polyethylene. So, the formation of polyethylene also, if it is metal catalyzed or some metal complex catalyzed, we should have some interaction with these orbitals with that of our metal. Similarly, for the corresponding CO bond, that means like that of our CC bond. So, this is the corresponding C and this is another C. Similarly, CO molecule can also be treated in a similar fashion, where the pi star orbital of the CO molecule, that we all know from our early days that how we construct the corresponding molecular orbital of the carbon monoxide molecule. It is involving the corresponding atomic orbitals of carbon and oxygen. So, we have no electron in the corresponding pi star level of the carbon monoxide molecular orbital. So, if that pi star orbital is available to accept the electron density from the field d orbitals of the metal. So, if the metal is present in low oxidation state or zero oxidation state, what we see that that particular metal, when it is interacting with this particular carbon monoxide, which is also a neutral molecule, but it has some power of acceptance of the electronic charge from the metal center, because it has vacant and matched pi star orbital. So, this vacant pi star matched orbital will be utilized for accepting the electron density from the metal side to the carbon monoxide antibonding level. Therefore, this carbon monoxide molecule is a well known and well accepted pi acceptor ligand. So, we know this whenever we write this carbon monoxide as a good pi acceptor ligand, but we have to now justify that within the spectrochemical series we have seen that carbon monoxide molecule is the strongest possible ligand within that particular known series for say 12 or 15 or 20 ligands we have arranged so far, and it is the strongest possible one, though it do not have any charge on it which can be utilized for the donation of electronic charge to the metal orbital, but only thing is that it has some symmetry adapted or corresponding pi acceptor orbital available for the acceptance of the electron density. So, in the low oxidation state of the metal, the electron density is pushed to this level and we get a very strong interaction between the metal and the carbon monoxide molecule. So, like that of our p orbitals, what we have seen in our previous slide, that if we have a single metal, say a single ligand center, single monoatomic ligand center, can be nitrogen, can be oxygen. So, p orbital was utilized for the corresponding donation or acceptance of electron density from the metal dxy or dxz or dyz, or rather metal T2g orbital which is filled. So, whenever we have ligand in metal, we having some electron or electron density in the T2g level of these orbitals, we always expect that it can show some push from this electron density from the filled metal orbitals to the empty metal ligand orbitals of pi star type. So, this since we do not have the matching symmetry, so this is pi star orbital what we have shown just now. And since we have this carbon atom bonded to this oxygen atom, so they are not going away to a long distance. Only thing that due to this antibonding, and if we have electron density in this antibonding level, our bond order is changing. That we all know that the electron density, if it is there in this antibonding level, the CO bond order will be diminished. So, if we push some electron density from the metal orbitals to this empty vacant pi star orbital of the carbon monoxide, which can show us that this carbon monoxide bond order will be decreasing and the carbon monoxide bond length will be increasing, and which can very nicely can be shown in terms of the corresponding stretching frequency in FTIR. The Fourier transform infrared spectroscopy can be utilized to detect that interaction. So, that basically shows if we compare with the bare molecule, that means the free carbon dioxide molecule as a gas, and if we can use the gas cell for monitoring the corresponding absorption spectrum in FTIR, we can measure the corresponding stretching frequency of this carbon monoxide molecule. And if we now compare that stretching frequency and following Hooke's law, we can show that the corresponding bond order between carbon and oxygen has been reduced, and carbon oxygen bond length, which is also well known to us, is also changed, and which having now longer bond distance between carbon and oxygen. That means definitely the electron density from the filled metal orbitals of T2g symmetry has been pushed to these empty pi star orbitals. So, what we have? We have the filled d orbital on the left hand side, and on the right hand side the empty pi star orbital from the carbon monoxide molecule. So, we get these. So, from this particular diagram we have so many informations in our hand that carbon monoxide is behaving as a good pi acceptor ligand. It is accepting the electron density from the metal side, and the corresponding bond order is getting changed, which is reflected in the corresponding stretching frequency, the CO stretching frequency in FTIR, and the corresponding empty pi star orbital is being utilized for very strong interaction between the metal and the ligand. So, in a similar fashion, if we are able to utilize these pi star levels from the ligand side for interaction, we should have the corresponding interaction which is of pi type but on opposite orientation. That means the ligands are now good pi acceptor ligands. So, now we will see how this interaction can have some direct effect on the corresponding crystal field strength or the ligand field strength of this particular ligand. That is why we are placing this carbon monoxide molecule towards the right end of the spectrochemical series, where we consider it as a very strong ligand compared to the other known ligands. So, what we see that the other type, what is the corresponding pi donor ligands. So, the carbon monoxide molecule, what we can see that it is the corresponding ligand system where it can accept the electron density from the metal. So, it is behaving as a pi acceptor ligand. But before discussing in detail and the molecular orbital picture for those interactions, what we can see now the corresponding pi donor ligands from the ligand side. So, this particular orbital what we can have the CC bonding interaction or the corresponding CO bonding interaction for this particular figure, what we see that if we have the ethylene molecule, and after overlap we have typically more or less a banana shaped electron density of this type, and this electron density is of pi type, and if our ligand is a pi donor ligand, that means ethylene now can function as a pi donor ligand. So, it will donate the electron density to the metal vacant orbital, and this orbital like the equivalency of the pi star with the dy orbital. So, this will also have some equivalency with that of our p type orbital. So, it can very nicely be utilized for corresponding donation. So, as we all know that the p orbital, if it is in this particular direction, if it is the corresponding x direction or y direction, if it is x direction it is the py orbital. So, it has the corresponding matching symmetry with the px orbital. So, like that of our oxygen or nitrogen, the field electron density from the px orbital is being donated to the metal center. Similarly, this ethylene can function or can donate the electron density to the metal orbital. We have the metal ethylene interaction, and in some good complexes we know, which is known as also the corresponding Vasquez complex, where this particular transition metal center is being utilized in presence of some other groups like carbon monoxide, that ethylene group is there, and the corresponding distance between this metal center with that of our ethylene is the corresponding same distance. This is basically these two MC distances are same. So, in perpendicular orientation the ethylene molecule is bonded to the metal side. That is why the pi electron density which is in between the carbon-carbon axis is being utilized for the donation to the metal center. We do not have any direct bonding to any one of the carbon, whether it is C1 or C2. So, we do not have any bonding interactions with the C1 or C2 with that of the metal center. So, we can have the corresponding interaction. So, if we go for the pi donor ligand system, that means the pi type electron density is available from the ligand side to donate that particular electron density to the metal orbital which should be vacant. So, ligands which are mostly that sigma donors, but we can have some other ligands where we can consider them as pi donor ligands. So, the ligands of this type, when only the sigma donor electron density, that means the sigma electron density is utilized, and in most cases these electron density, if the electron density is available from the water molecule or ammonia molecule, they are basically initially the non-bonding electrons. But if there is non-bonding electrons are giving rise to the head-on overlap with the metal orbitals, we get this particular interaction is of sigma type, and we consider them as good sigma donors. But if we have filled p and d orbitals, so if we have some more filled p orbitals and more d orbitals not from the corresponding sigma type orbitals, so they can serve as good pi donor ligands from the ligand side. So, what type of orbitals we can have for pi type donor is the pi type donor is the iodide ion, chloride ion, and the sulfide ion. So, these are of bigger type of atoms. So, they all have the d type orbitals for the filled electron density, and those filled electron density from the d level as well as some of these p levels are utilized as pi donation to the metal center. So, they interact basically with the T2G set of orbitals on the metal to form the bonding and antibonding molecular orbitals. So, we will allow these p and d orbitals from the ligand side to interact with the only to the T2G set of orbitals. So, what we have earlier we have seen when we are talking about the corresponding transitions for sigma type interactions, this T2G was remaining as the corresponding non-bonding level, and this particular non-bonding level was utilized for only that electron density transfer from this non-bonding level to Eg star level. Now, the same Eg can show some pi interaction apart from the sigma interactions what we can have already. So, in this molecular orbital diagram in octahedral geometry for an Ml6 complex formation, what we see is that apart from sigma bonding interactions, we are allowing the corresponding pi type interaction from the T2G set of orbitals and the metal pi orbitals of this. So, if we have 3 such labeled orbitals, so we can have the 3 orbitals of pi symmetry, and these 3 orbitals of pi symmetry which is matching with T2G, say that means from the reducible representation we can take out the irreducible part of T2G symmetry. So, the T2G symmetric orbitals from that representation will now overlap with the metal T2G side to giving bonding as well as anti-bonding orbitals of this type. And if only the pi levels are filled, that means the ligand is functioning only as a pi donor ligand, like our iodide, like our chloride or sulfide. So, if they are our ligands, then this can serve as a good pi donor ligands, and since they are good pi donor ligands, they will interact with the T2G level of metal ion orbitals and they give rise to 2 levels, and the metal electron is being pushed to the corresponding T2G antibonding level. So, we have now this, though this is an antibonding level in terms of the corresponding molecular orbital picture in LFT, but this can be the ground state because we have the corresponding Eg level above. So, in terms of the corresponding sigma interactions, we have seen that the Eg star, this was rather Eg star level which was above the T2G level, where T2G level was non-bonding level, but this was the Eg star level. So, now when we start going for the corresponding pi interactions, this particular level is now the ground state level and your Eg star level is utilized as the corresponding level which is lower corresponding LUMO level, and that LUMO level can accept the electron from the T2G antibonding level after pi bonding interaction. So, these are the slight modifications what we are getting due to the pi interactions from the ligand side, and we are all the time we are restricting our attention mostly to this particular region because this particular region is very interesting to consider the corresponding ligand field strength or the crystal field strength, that means the delta O, in terms of arranging the different ligands in the spectrochemical series. So, we have this much gap what we are getting, that means what the gap was this much before interaction and this gap is reduced after interaction. So, if we have pi donor orbitals in our hand, so the energy gap is getting lowered. So, we are not getting any such ligand system which will be strong enough in terms of the corresponding ligand field splitting energy or ligand field stabilization energy. So, in terms of both crystal field and the ligand field term, the corresponding gap is being reduced if we can have a corresponding pi donor type of ligand. So, what we see therefore, the bonding orbitals which are lower in energy are primarily therefore filled with the electrons from the ligand, because this particular orbitals are 3 in number from the ligand side, the T2G set. So, they are basically pi type filled, and the antibonding molecular orbitals are primarily occupied by electrons from the metal. So, this is the corresponding antibonding orbital after pi interactions. So, these antibonding orbitals are of metal type and these bonding orbitals are of ligand type. So, therefore, this antibonding metal type T2G star orbital is available for transfer of electron density from this level to that level, that means T2G star to EG star level. So, these orbitals are therefore being utilized for this type of interaction. So, what we can have therefore that this gap is getting reduced. So, if we have this delta octahedral gap, that means this particular gap after this electron. So, this gap is being reduced due to the interaction which is of pi type. So, the size of delta O decreases since it is now between an antibonding T2G orbital, that means T2G star. This the level of this would be T2G star. This is T2G after ligand field formation, and this is T2G star and the EG star orbital. So, this transition whatever we are considering after pi interaction is the T2G star to EG star level, and this pi star level for the corresponding pi interaction with the metal orbital is well above in the energy scale, and they will remain empty in this molecular orbital diagram. So, this basically confirms the corresponding position of these ligands like iodide, chloride and sulfide in the spectrochemical series, and basically what we are getting over there as weak field ligands are also pi donor ligands. It is not that if we have any kind of pi interactions that they will be strong enough. So, our notion for all the type is that if we have any kind of pi interaction, the ligands would be strong enough, but it is not with the pi donor ligands. It is true for pi acceptor ligands that we will discuss in our next class, that these pi acceptor ligands will modify the corresponding splitting energy for these two levels, but the donor ligands can only reduce the splitting and will be on the left hand side of the spectrochemical series where they are considered as the corresponding weak field ligands. So, in case of these pi acceptor ligands like that of our carbon monoxide molecule, what we will see that this metal center is available and we have the carbon monoxide molecule, and if we get this electron density is coming from the carbon monoxide, this is the corresponding type of donation, and if the corresponding orbital which is available from the carbon monoxide depending upon the corresponding molecular orbital of the carbon monoxide molecule. So, if they are of sigma type, so our carbon monoxide molecule can be termed as sigma donor orbital. So, when we talk in terms of the corresponding molecular orbital of sigma symmetry, we can place this carbon monoxide molecule for sigma donation, and as a result we can have both the sigma bonding level as well as sigma antibonding level as the star level, and the electron density from this field level is being donated to the metal orbital. When we consider the pi interaction, it is in the opposite direction. So, we have some vacant orbitals and now we know all that what are those vacant orbitals which can be utilized for a good acceptor orbital is our pi star orbital. So, if we have these pi star orbitals, what we have seen for the case of ethylene molecule, that this carbon monoxide molecule can have also the corresponding antibonding orbitals, and if these antibonding orbitals are utilized for acceptance of the electron density from the metal side, so metal will push the electron density from left to right, and then we can have this pi star level can be a good acceptor from metal dxy or metal dxz or metal dyz orbitals. So, now this particular interaction, that means the acceptance. So, this is the acceptance. If this is predominating for this sort of metal ligand interaction, we will consider the carbon monoxide as a pi acceptor ligand. Therefore, so they are the pi acceptor ligand. So, in our next class we will just discuss about this capability for pi acceptance. So, not only this particular one, but cyanide Cn minus obviously, then N2CO, they all have empty pi antibonding orbitals and matching symmetry for that interactions with the metal d orbitals, and they can serve as a very good pi acceptor ligands, and we will see how they can modify the corresponding splitting energy for the ligand fit. Thank you very much.